D.com, and we're going to do a little bit of reviewing before we get going today. All right. Oh, you're quiet today. I probably should enjoy that, but... Okay, today, ladies and gentlemen, we'll finish getting you caught up on the notes that I had the sub present to you, or the short video that, well, not short, the video we had the sub go through with you. A reminder, we're going to have our first quiz of this unit on Friday, okay? So what's going to be on the quiz, ladies and gentlemen? On the quiz will be graphing, potential and kinetic energy, heat and temperature, and a little bit on KMT. Now, I'm not going to make you make a graph, but I expect you to know the difference between a constant and a non-constant line on a graph, and I expect you to know the difference between an inverse and a direct line on a graph. Okay? Questions? All right. So the code you need for the Pear Deck, ladies and gentlemen, is this: QOLIRR. As long as you're logging in and I have your attention, ladies and gentlemen. Well, I can put grades on the report card starting very soon, ladies and gentlemen. Okay? Now, again, most of you have all of your stuff in. I have yet to start grading the density labs because I had to set up a lab for my other class this morning. So probably this afternoon and after school, I'm going to start grading your density labs. Again, if you are missing something, you need to go into Infinite Campus. You need to check. Now, I can tell you, most of you are not missing quizzes. Most of you are not missing tests, okay? Which is good. But there are some of you who may be missing some of the lab activities we did in the first unit. Well, if you turn them in, I will give you at least some credit for them, okay? Which is better than the no credit you have for them right now. So please, take a minute, go to Infinite Campus at some point in time, check and see if you are missing anything for me, okay? Questions? All right, so here we go, ladies and gentlemen. Let's review a little bit some of the things that we learned yesterday. Name the two factors that can affect kinetic energy. So what two things, ladies and gentlemen, can affect kinetic energy? So type in your two answers, please. Now again, ladies and gentlemen, if you took physical science here at East High School, during the physics part, they talked about kinetic and potential energy. They talked about a skate park, and they talked about energy pies, and how if you're going through a loop, your kinetic energy will change and your potential energy will change. We are not going to go that crazy in this class, but we are going to talk about the factors that can affect your kinetic energy, and there are two of them. Give me one of them, Elsa. Max. Give me the other one, Karina. What's that? Okay. Giselle, do you know the other one? I don't know. Okay. Think about the lab we did yesterday, the activity with the books. Right. Velocity. Okay. So mass and velocity both affect kinetic energy, ladies and gentlemen. Okay. They both affect kinetic energy. And they are both in a direct relationship with kinetic energy, meaning that if you increase the mass, the kinetic energy of the object will increase. If you increase the velocity, the kinetic energy of the object will increase. But if you take two objects that have very different masses, shining and I, and we run a race, and we finish with the same kinetic energy, because I will say this as nicely as I can, because I'm much more massive than Shining is. Shining has to move faster than me. It is the only way she and I can have the same kinetic energy. What I have over her in mass, she needs to make up for in velocity. So if we finish a race with the same kinetic energy, she wins the race because she will have had to have moved faster than I did, which meant the distance that we were going to run in a race, she is going to cover it faster. Now, if Ray and I finish a race tied, means we had to have the same velocity. That's the only way we could finish the race tied. Ray and I are not the same mass. Once again, I have a little bit more mass than, okay, I got a lot more mass than Ray, but let's not get into that, okay? Meaning that if we finish the race at the same velocity, I have to have more kinetic energy than he does because I have a larger mass than him, okay? That is all the stuff about kinetic energy that hopefully you need to know. Questions? Good, wonderful. Name two factors that can affect potential energy. There are actually three. Please do not name the one that we cannot change. So there are three things that will affect how much potential energy an object has. All right, Zach, name me one. Height. Height affects potential energy. Finley, name me the other. Mass. Can someone name me the one that we cannot change? Gravity. Okay? So, all of these boxes are up here. Most of them are at the same height. We won't count the ones that are on top because obviously they're a little bit higher. Okay? These two boxes are empty right here. Which one has more potential energy? These two right here. Which one of these two has more potential energy? The one on the top, because it is higher up. Now, of all the ones that are level here, which one would have the most the most potential energy? The one that is the heaviest. Again, it might be the binders and rulers, but I doubt it because there's aluminum cans in there. Okay? There's one up here that used to be marked somebody's cat. I don't have a cat in it, trust me. Okay? Why was it? I don't know why they marked it for somebody's cat. I didn't mark it. They did. Leave me alone. Are you sure? Positive I've lost 2 electrons. Actually, probably the heaviest or the most potential energy up here is this box right here. It has a bunch of model kits in it. It's the heaviest box there. But again, potential energy depends on how heavy the object is or its mass, better term, and it depends on the height of the object. Okay? So, again, those two things affect potential energy. Gravity also does, but you and I are going to probably be bound to this planet for the rest of our lives. So we are stuck with the gravity that we have here unless we somehow colonize another planet and you get to magically go there. Okay? Sam? Yeah, put away your phone, please. Or Kevin, sorry. Put away your phone, please. Okay? I don't want to see them, ladies and gentlemen. If they're out, put them away now. The next one gets put in the cabinet. All right, so mass. Told you I was a big fan of cutting and pasting, right? Apparently, I forgot to change the answer key there. Okay. You can't answer this one yet. We haven't talked about that. So let's stop there, ladies and gentlemen. Let's stop there. All right. So today we need to cover something called KMT. Yesterday we talked about two laws. What were they? Good. I'm glad I was memorable yesterday. Thank you. The law of conservation
of mass
and energy. The law of conservation of energy. Laws are irrefutable. They can be mathematically proven. They happen over and over again without doubt, without question. Theories, ladies and gentlemen, are not irrefutable. Theories are the best explanation of something that we see based on the evidence we have. There is a theory in chemistry called KMT. KMT stands for kinetic molecular theory. Now, first of all, there's one thing I want to point out to you. Parts of this theory are 100% true and accurate. Parts are questionable. And they're only questionable because we have never gotten certain things to happen. Okay? So, again, a theory is the best explanation after years and years of science, and we come up with the same basic conclusion. But unfortunately, there is not enough evidence to actually prove it and make it into a law. Okay? So that is the difference. So there is a theory called kinetic molecular theory. Now, when you were in physical science or when you were in 8th grade or 7th grade or whenever they taught you the chemistry portion down in middle school, they talked to you about the states of matter. Okay? What are the 4 states of matter? What? Gas, solid, liquid, plasma. Very good. Now, of those 4 states, we are going to ignore one almost completely. Plasma. Okay? Why? Because it is the least abundant form of matter here on Earth. Least abundant. Fire is plasma. Lightning is plasma. Basically, that covers most of it on Earth. Okay? So we're going to concentrate on solid, liquids, and gases. And we are going to look at them from the view of kinetic molecular theory. Kinetic molecular theory, ladies and gentlemen, has 2 points. Okay? And it's the basis for how we're going to look at chemistry and how we're going to look at states of matter and how we're going to look at how matter and energy interact with each other. 2 points. Point number 1, all matter is made up of tiny particles. Your desk in front of you is actually made up of tiny, really small particles. What do we call them? What? And you are correct. Atoms or molecules. There, ladies and gentlemen, above your heads. There, ladies and gentlemen, on that wall. There, ladies and gentlemen, on that wall. There, ladies and gentlemen, on that fume hood. There, ladies and gentlemen, on that fume hood are lists of all of the atoms. All of the elements that are on Earth. And there are 118 elements on that list, but only 92 of them occur naturally on Earth. After 92, after that element right there, after uranium, everything else is made in the laboratory somewhere. It is synthesized, it is man-made. We take 2 smaller atoms, we smash them together, and we get bigger atoms. Doesn't occur naturally. The other 92, you can go somewhere on Earth, you can find them either alone or combined with other elements to make a compound, molecules, and they're around us. Okay? First 92 are naturally occurring. They make up everything around us, ladies and gentlemen, either alone or in combination with some other elements. Then we call it a molecule. Okay? All matter is made up of tiny particles. That's not the theory part. This is. Those tiny particles are in constant motion. They are always moving unless we get to what temperature? Absolute 0. And the reason it's still a theory is because we haven't gotten matter to absolute 0. We haven't gotten matter cold enough to where we stop this motion. Okay? By the way, if you are constantly moving, you constantly have what? Constantly have kinetic energy. Constantly have kinetic energy. All the time. Questions? All right. So, this is probably the solid, liquid, and gases information that you were given in physical science in 7th grade. What year did you guys take it in middle school? Anybody remember? 7th? Because I think 8th was like earth science.
Yeah.
So 7th was it life? It might have been physical science, life science, then earth science. So it might have been 6th. Anyway, ladies and gentlemen, they probably gave you something that was like this. The way we define solids, liquids, and gases, ladies and gentlemen, is what we call a Newtonian definition. It's based on whether things have a definite or no definite volume and shape. And it allows us to separate the 3 states of matter. And if an object has a definite shape, like that, it can be a solid. Definite shape means it's going to hold its own shape no matter what kind of container you put it in. Now, before we get crazy, people go, well, Mr. Brand, you can take a hammer and smash that and change its shape. Yes, you can. But then it will hold that new shape. Okay? It will hold that new shape. That's all definite shape means, is it holds its shape on its own. Solids also have a definite volume. They take up a certain amount of space. If you go to liquids, they have a definite volume. They do take up a certain amount of space, but they take the shape of whatever container they are in. The liquid in this bottle is taking the shape of the bottle. But if I squeeze it, it will then take the shape of the straw to come flying out of the bottle. It can change its shape. So we say it has no definite shape. It does have a definite volume. Liquids always take the shape of their container. Always. Gases have no definite shape and no definite volume. And more importantly, ladies and gentlemen, gases will completely fill their container. So gases, if they have a chance, they will spread out and they will completely fill the container up. Completely. Okay? Now, in terms of motion, solids normally have the slowest motion, and all they can do is literally vibrate back and forth. Now, if we were to do this, which we won't, if we were to take this row and slide them over until your desks are literally touching this middle row, and then did the same with you guys, no one would really be able to move much. You would be able to sit in your seat, move back and forth a little bit, but you wouldn't be able to get out. That's what the particles are like in a solid. They are packed tight and packed close together. So all solids can do is vibrate back and forth. The particles, the tiny particles that make them up. So we will never see it, but the particles in this desktop, the particles in your desktop are vibrating back and forth right now. In a liquid, they spread out a little bit. They are more semi-free, okay? If Alicio wants to walk to the front of the room, there's room for him to come up and do it in between you. That's what the particles are like in a liquid. There is room between where the particles can move and slide past one another, okay? They can move and slide past one another. They're moving a little bit faster and they are semi-free. I always said a liquid is like taking a dog for a walk on a leash. The dog is on the leash. Can it be in front of you? Can it be behind you? Can it move around you? Sure. What happens if the dog tries to go too far? You're going with it. So you got a little chihuahua and it takes off and you're going with it.
There's going to like
okay, it's going to get pulled back. There's something that keeps it from getting too far away, right? Well, that is what exists in liquids. There are these things called forces of attraction. They exist and they hold the liquid in a liquid form. They exist in a solid too. And that's why the particles stay in one place or stay near one another. There are forces of attraction that hold it together. But in a gas, ladies and gentlemen, these particles get completely free of each other and spread out as far as they can. Matter of fact, the gas particle, if there were one in this room and it were moving this way, it's going to continue moving this way until one of two things happens. It either gets all the way across the room and hits the wall and then it's going to bounce off it and bounce back, or if it hits something along the way. What could it hit along the way? Other gas particles. Who knows? Maybe one comes right now and hits right square in the forehead and bounces off and goes a different direction. But it's got to hit something. Gas particles move in a straight line until they hit something, then they bounce off in other directions, which is why if it's moving this way and somebody opens the door, it goes right out the door and keeps going until it hits something. Okay? Now, in terms of energy, solids normally have the lowest energy. Why? Because they're moving the slowest. Liquids normally have a medium energy. Why? Because they're somewhere in between. and gases are the most high energy state. Now, just to cover it, plasma is even a higher energy state than gases. Gases, the particles move incredibly fast. In plasma, there is so much energy that the particles, which are atoms, literally get electrons ripped away from them. And it separates into what we call ions, a positive ion and negative ions. That's what a plasma is, real high energy state of matter. Okay? All right. You guys have all seen this before. States of matter, solid, liquid, and gas. Okay? We call it melting. By the way, the more scientific term for melting in chemistry is fusion. So they will talk about the heat of fusion, and that is the energy it takes to melt something, to go from a solid to a liquid. From a liquid to a gas, ladies and gentlemen, that is boiling or vaporization. And from a solid to a gas, that is a process called sublimation. Now, what is red? When you see red and blue, what do they normally indicate? Hot and cold. And that is exactly what they are doing here. The red, the inside lines, require us to add energy to get from a solid to a liquid or a liquid to a gas. Or even to go directly from a solid to a gas. We have to add energy. If I take an ice cube and put it on this counter, what's it going to start doing? Wow, who knew that was going to be the hard question of the day? What will an ice cube start doing if I put it on the desk here? Melting. Why? Well, ice cubes are stored in our freezers. Our freezers are set at a very cold temperature, below 0 degrees Celsius. We put it out of here, the room temperature is 20 degrees Celsius. That is a hot enough temperature so that a solid water will start becoming a liquid. That phase change is called melting. We're adding energy. Now you may say, well, we're just putting it in the room. You're not heating it up. By putting it in the room, that is heating it up from where it's at when it's in the freezer. Okay? Now, all of these have an opposite process. Freezing, solidification, or crystallization is going from a liquid back to a solid. Condensation is going from a gas back to a liquid, and deposition is going from a gas back to a solid. Not a lot of things do these. Skipping this liquid state, but there are some things that do that. And even some common things under the right conditions. Water vapor in the air, if it gets cold enough overnight in the right conditions, will form frost directly on a car window. It will skip the liquid state entirely. It will go from a gas to a solid on a windshield. That is deposition. Okay? That is deposition. All those things are in blue. Why? Not because they're cold. By the way, can we add cold? No, you can't. There is no such thing as adding cold. However, you can remove heat. You can take heat away. When you put something in the refrigerator, when you put something in the freezer, it is a colder environment there which takes the heat away from whatever you put in it. You put water in the freezer, it takes the heat away and it makes it ice. You cannot add cold, but you can remove heat. The term for removing heat is exothermic. The term for adding heat is endothermic. Now, very few numbers in chemistry are ever negative. However, if you are adding heat to something, we normally refer to that as a positive value. If you are removing heat from something, that is normally then a negative value. Not because it's a negative amount of heat, but the positive and negative sign indicate the direction in which the heat is moving. Questions? Wonderful. Now, if you don't like that diagram, ladies and gentlemen, here it is written out as a definition. It means the exact same thing as on the last slide. Freezing, crystallization, solidification, the process of going from a liquid to a solid. Fusion, the process of going from a solid to a liquid. All I did here was write them out as definitions instead of putting them in a diagram where you could see what they were going through, what changes. There is a term here on the bottom, though, that people often confuse with boiling and vaporization, and that is evaporation. Evaporation is a different process, ladies and gentlemen. Evaporation is occurring in the back of the room right now in all of our containers of water. Evaporation is occurring on every lake, river, and stream. Any place where there is water on the exposed to the environment. Okay? Evaporation is occurring. Now, what is the difference between evaporate? By the way, half of these processes are exothermic, half are endothermic, same as before. So, real quickly, the difference between evaporation and boiling, ladies and gentlemen. Evaporation is going from a liquid to a gas, but it only occurs at the liquid surface. Boiling changes from a liquid to a gas, and it occurs throughout the entire liquid. Evaporation, no energy is needed. Boiling, you add energy. Evaporation happens only at the surface. Boiling actually happens at the spot closest to the heat source, which is normally the what of the container? The bottom. That's why we see bubbles come up through it, because they have to get from the bottom, where they became a gas, to the top, where they can escape and go into the atmosphere. Evaporation, only some of the particles can do this. Boiling, all of the particles can. So not every particle that's on the surface evaporates. Only certain ones. We will explain why. Questions? Okay, some people are typing, so I'll give them a second. Anyone need more time? Okay. There is a difference between heat and temperature. There's a very distinct difference between them. Now, before I ask you the difference, I've got a math question for you, ladies and gentlemen. What is the difference between the sum and the average of numbers? Sum, you just add them all up, right? Get a total, correct? What is an average? So in an average, we still add them all up, but then we divide them by how many there were, correct? Okay? So, in a sum, the number of values matters, correct? Because we're adding up all of the values. In an average, does the number of values really matter? Yes or no? In an average, does the number of values really matter? Not really. Because however many values there are that you added up, what do we do with them in the end? Divide that. So if we divide by 10 because there's 10 values, or we divide by 20 because there's 20 values, we're getting an average for one value, right? Okay. That, ladies and gentlemen, is the difference between heat and temperature. That, ladies and gentlemen, is the difference. Heat is a measure of the sum of kinetic energy of particles of matter. Heat is the sum of kinetic energy, which means we do what to them? Go ahead. We add them all up. We add them all up. Okay? Kinetic energy still depends on what two things? Wow, I was hoping we would do better than this, considering this was the first question we started the day out with. Kinetic energy depends on what two things? Mass and velocity. Giselle, catch. Charles, look out! You ready? Okay, Giselle, catch again. By the way, which throw had more kinetic energy, would you say? Here we go. Ready, Giselle?
Yours.
Why?
Because you threw it high.
Nope. Why would one throw have more kinetic energy than the other? Because what can't I change about this object? I don't care about gravity. Gravity has nothing to do with kinetic energy. It's mass. The two factors that affect the kinetic energy of an object are its mass and its velocity. The only thing that you could change about this object to change its kinetic energy is to change its shining. Look out. Now you're going to throw it back to her. She already dropped it once. Watch her head because she's throwing it now. The only thing we can change in this object is how fast it's moving. I cannot change its mass. Correct? So think about that in terms of particles of matter. What can you change about particles of matter and what can't you change about particles of matter? The particles in this desk. What can I not change about them? What? The amount and the mass. Now, I really don't care about amount because it doesn't affect kinetic energy, correct? But I do care about their mass because mass is one way I can increase kinetic energy. If I increase the mass of an object, it has more kinetic energy, correct? Can I increase the mass of the particles in this desk? So what is the only way I can make them have more kinetic energy? Change their velocity. How do I change their velocity? How do I get the particles in that desk to start moving faster? I heat it up. I heat it up. I heat it up. The particles in this desk start moving faster. Because their what has to increase? And kinetic energy. Kinetic energy. Heat is the sum of the kinetic energy in here. Now that does depend, as Evelyn said, on the what of particles? Amount. Why? Because I'm summing them up. I'm saying there's this many particles. They each have this much kinetic energy. I add them all together. There is a certain amount of heat in this table. Heat. Right? Which contains more heat? The table or that cup? Why? Okay. What temperature is that cup? Really? What temperature is that cup? Room temperature. What temperature is this table? Yeah, why would it be hotter than room temperature? Nobody's been sitting on it. Name me something in this room that is not at room temperature. Your chairs. Why? Because you have heated them up. So what else is not at room temperature? You are not at room temperature. Give me something else not at room temperature in this room. Your chargers, your computers. Feel the back of your computer, the underside by the battery. I guarantee you it's warm. What else? Your water bottle? The outside or the inside? Okay, the inside, I will agree. Is the outside, do you think, room temperature? Okay, then it's a little bit cooler than room temperature. Good. That's one that's not. Come on, give me something else. Not room temperature. The lights! The lights are over room temperature. Give me something else. Not at room temperature. Need to stretch a little bit this morning. What? Good! The projector's not at room temperature. Matter of fact, the projector has a what on it? Has a fan on it to try to cool it down. Make sure the bulb lasts longer. Otherwise, everything else in this room is at what temperature? The water in this container, the sanitizer in here, the tissues in this box, even the pipe on this wall is at room temperature. The floor, the desktop, well, okay, maybe not this one whiteboard. Why? Projector's shining on it, but the other one's at room temperature. Okay? Does every one of those objects have the same amount of heat? Let's go back to it. Does that can and that tabletop have the same amount of heat? No. Why not? One of them has more particles. This desktop has a lot more particles in it. This can has few particles in it compared to the desktop. They're at the same temperature. This has more heat than this. Simply because there's more particles here. Okay? Now, what is the same about these two? They are at the same temperature. What is temperature? Temperature is a measure of the average kinetic energy in the particles of matter. The average kinetic energy in particles of matter. That depends on the mass of individual particles and the speed of the particles. So both heat and temperature, I'll go ahead and type. One word makes a big difference in these two definitions, doesn't it? Sum, average. Because the word sum is in here, the number of particles now matter. Because the word average is here, the number of particles doesn't. The number of particles no longer matters over here. But again, still, the only way to make something increase in temperature is to change its kinetic energy. And what is the only thing you can do to matter to make its kinetic energy increase?
Heat it up.
Which causes what to happen?
The particles to move faster.
Particles to move faster. You want to increase temperature, you have to add heat. You add heat, you cause the particles to move faster. Particles to move faster increases kinetic energy. That is the only way to change the temperature. Okay? That is the only way to change temperature. By the way, are there a lot of particles in here? Yes? No? Maybe so? Does that mean they're all moving at the same speed? Is it possible that some are moving faster?
Yeah.
Is it possible that some are moving slower? But all we do is take an average, ladies and gentlemen. The faster ones cancel off some of the slower ones. Most particles are moving at around the same speed, but it is possible to have some that are faster and some that are slower. Absolutely. Absolutely. Okay? Heat, temperature, and KMT. If your temperature is going to increase, the particles must move faster according to KMT. That is the only way to make the temperature increase, to make the particles move faster. You cannot change the mass of the particle. Impossible. Cannot be done. Okay? Heat must also increase. Why? Because if the particles are moving faster, their heat is going up as well. Okay. Thank you. Okay? Each particle's energy increases. That increases the total amount of heat. Because in heat, what can't I change about this? What can I not change about this tabletop?
Mass.
The mass and also how many what?
Particles.
I can't change how many particles are here, right? I can't suddenly add particles and put more in here. I can't make fewer, correct? So the mass of the particles and how many are not changing. So if you add heat, the only thing that can happen is the particles have to move faster. The particles have to move faster. By the way, this is a direct relationship. If temperature increases, heat also increases. By the way, what's the other direct relationship to? If temperature increases, heat increases, what else increases?
Kinetic energy.
Thank you. Kinetic energy. Kinetic energy also increases. If temperature decreases, the particles must move slower. The particles must move slower. Since we cannot change the mass of the particles, that is the only way temperature can decrease in a substance. The only way. Okay? We cannot change the mass. Heat also has to decrease. Each particle's energy decreases. That it decreases the total amount of heat. Okay? And again, ladies and gentlemen, that is still a direct relationship. By the way, you decrease temperature, you decrease heat. What else do you decrease? The kinetic energy, which means the particles have to move what if kinetic energy is going down? Slower. That's the difference between physical science and now, ladies and gentlemen. You need to put all four of those things together. Temp goes down, heat goes down, kinetic energy goes down, speed of the particles goes down. All four of those things happen together. Why? Because you can't change the mass. And you can't change the amount of matter in there. All right. How is it possible for a cold object to contain a large amount of heat? How is it possible for a very cold object to contain a large amount of heat? Correct. It has a large amount of particles. An iceberg has an incredibly large amount of heat, ladies and gentlemen. Not because it is incredibly hot, but because it is incredibly large. And heat, we do what to our numbers? We do what to our kinetic energies? Starts with an S, ends with an Sum them up. So this object has a lot of heat, not because it is hot, because there is so much mass there. Okay? How is it possible for a small object to contain a large amount of heat? It's got to be incredibly hot. The particles have to have a lot of kinetic energy. Something like lava. Okay? Something like lava. A small amount of liquid lava has a lot of heat because it is incredibly hot. Not because there's a lot of it there, but because it is incredibly hot. Why? Because heat depends on how much is there and what temperature it's at. Okay? Questions? Good. Wonderful. Two substances are at the same temperature. Oh man, now we got the baby and the linebacker running a race again. Two substances are at the same temperature. Explain how these substances could have their particles be at different speeds.
If one of them was colder than the other. Oh, larger.
Now remember, it says both objects are at the same temperature. Okay? How could those objects, how could their particles be at different speeds?
One of them has more mass.
And then the particles would move how? Think about it. You have heavy particle, you have a light particle. To be at the same temperature, they have to have the same See, you're not making the connection. They have to have the same kinetic energy. Now, because these are two different particles, the particles do not have to have the same what? Starts with M, ends with, never mind. What? Mass. Okay? So these two particles do not have to have the same mass because they're not the same thing. So now you got the baby and you got the lineman. Okay? To be at the same temperature, they have to have the same kinetic energy, correct? The baby is lighter, the lineman is heavier. How does the baby have to move compared to the lineman? Elsa, go ahead. If you're going to, I kind of heard it. What? Faster, thank you. Smaller particles move faster at the same temperature as larger particles. Because their kinetic energy is the same, one is larger than the other. How is it possible for frozen ice cream to have the same heat as boiling water? How is it possible for frozen ice cream to have the same heat as boiling water?
Same mass, or like amount of particles.
But if there's the same mass of each, how do we get heat? We do what to their kinetic energies? No. Don't go there. How do we find heat? It is the what of kinetic energies?
Average.
No. Temperature is an average. Heat is the sum. So how can ice cream and boiling water have the same amount of heat? No, if they do, I guarantee you the ice cream is going to have less heat. If they both have the same amount of particles, how can the colder one have as much heat as the hotter one? Which is? There has to be a larger amount of ice cream. There has to be a larger amount of ice cream. Why? Each piece can be moving slower, but if there are more pieces, that can even out. That can even out. So, boiling water, a very little bit. Cold ice cream, a lot of it. Still have the same amount of heat. Still have the same amount of heat. Questions? Wonderful. How many of you remember this from physical science? Nobody remembers this graph? Would it help if I told you you only saw from about here to there? It's the heating curve of a pure substance, ladies and gentlemen. This is what any pure substance just means only one thing is there. One thing is there. And this is the heating curve of a pure substance. Okay? Now, when a substance starts out in its coldest, what state will it be in? When a substance is coldest, what state will it be in? Solid. So that area A, ladies and gentlemen, right there represents where it's a solid. So this area down here represents where it's a solid. Okay? If this is a solid down here, ladies and gentlemen, what state of matter is it in up here? Nope. What does it go from a solid to normally? Solid to a liquid. Okay? Goes solid to a liquid. So what's happening at area B between when it's a solid and when it's a liquid? What has to happen for a solid to become a liquid? Has to melt. So in area B, there's a phase change going on. Melting, going from a solid to a liquid. Area C is where it is a liquid. So what state of matter is it in up here when it's hottest? It's a gas. So what has to happen here at D? Has to boil. Has to be a phase change, boiling or condensation, and then at section E, it is a gas. Okay? Now, I don't care what substance you are talking about. This could be water. This could be rubbing alcohol. This could be glycerin. This could even be steel. Can I melt this pipe? Yeah, I got to put a butt-ton load of energy into it. About 1,568 degrees, but it will melt. Can I boil this pipe? You bet I can. It takes about 3,200 degrees. And this iron will start to boil and become a vapor. It would look exactly like this one does. The only thing that changes is the slope of those lines, how long they are, that's it. That's the only thing that changes. Now, here's the question. What's that made out of? Can you melt wood? You cannot melt wood. What happens if you try to heat wood up? It burns. It turns to ash, right? Not every substance can do this. Wood doesn't have a heating curve like this. Why? Because you can't get it to change into another state. Instead, it chemically breaks down. You break the chemical bonds that make it wood, and it becomes now carbon, water vapor, carbon dioxide. It is no longer wood. This substance, whatever it started out as here, alcohol, water, glycerin, iron, I don't care, it's still that same thing up here. So any substance that can go from being a solid all the way to being a gas, this is what it will look like, ladies and gentlemen. That is the basic shape that a heating curve will have. Okay? So now let's talk about some information we can get out of it. To get from here to here, what do you have to do? What is constantly being added in this diagram? Heat. Heat is the way we make something go from being a solid to being a gas. Now, In this area here, what's happening to the solid? When you're adding heat to the solid, what is actually happening to it? What? Nope, not yet. Thank you. Which causes the what to increase? By the way, for those who didn't hear Abby, heat is making the particles move faster. If the particles move faster, what is going to increase? And that will cause the what to go up? The temperature. And that is what we are seeing in here. We are adding energy. This temperature is going up because the particles are moving faster. Are we still adding energy here? 5 kilojoules, 10 kilojoules. Did we still add energy there? It's not a trick question. Think about it. To get from here to here, how much energy did we add according to this diagram? To get from one end to the other, how much energy did we add? 36 kilojoules, correct? Is there any time in there that we're not adding energy? Is there any time in there where this graph is not moving from the left to the right? So we are constantly adding energy, aren't we? Here, that energy goes to making the particles move faster, increasing their temperature, correct? What happens from here to here? Here it's a liquid. What happens when it's a liquid? When you add energy, what happens? So, hang on. There we go. Do, 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 do. The only way to get, come here. Sorry, ladies and gentlemen. My thing is out of juice. All right, the only way to get from here to here is to do what? What do I have to do? I have to add energy, right? Is there any time in here where I'm not adding energy? Good. We got that established. Good. Let's agree with that. Good. Let's go from there. So now, ladies and gentlemen, let's take a look at just this area down here. Okay? So down here, ladies and gentlemen, I am adding energy. What is happening to our substance down here? What is increasing? Temperature is increasing. Why does the temp increase? Okay? Because kinetic, and I'm just skipping a step here because you actually went ahead of where I wanted to go, Cameron. Kinetic energy goes up, which means the particles move faster. Right? Because we go from a temperature of just above 0 to a temperature of somewhere around 40. Temperature's going up. Particles have to move faster because of that. Okay? Good. So now what happens in this area? What? Temperature goes up? Why? Same thing that happened in A is happening in C, correct? Okay. So, adding energy, temperature goes up, kinetic energy goes up, particles move faster, correct? Good. All right, one last area then. This area up here. What is happening up there? The same exact thing in all three of these areas, correct? Now, down here, A, we are a solid. C, we are a liquid. And D, or E, we are a gas, correct? Okay, good. Now, what happens here? Are we still, number one, adding energy? Okay, so we are still adding energy. Okay, questions? All right, good. Hang on a second. Okay, what's happening to temperature? What's that? It's increasing? Temperature is constant. What does that mean? What is it? Why? Why isn't the temperature increasing? Okay. But for temperature to be constant, what does that mean for kinetic energy? If it slowed down, what would happen to temperature? Kinetic energy must be the same, correct? Which means what happens to the particle's movement? So in this area, even though we're adding heat, the temperature isn't going up, the particles aren't moving any faster, and the kinetic energy isn't increasing, correct? What about up here? What? You bet. That's the same thing. So here's my question for you. Where's the energy going? In here, when I add energy, I can see where it's going. It's going to make the particles do what? Move faster, increase their speed. Kinetic energy go up, correct? In here, particles are moving faster. Kinetic energy is going up. They're speeding up. That makes sense, doesn't it? If you heat something up, shouldn't the particles move faster? Right? How come here the particles don't move faster? Where's the energy going? Law of conservation of energy. Energy cannot be created or destroyed. You're adding energy to it. Where is it going?
It's changed.
What do you mean it's changed? Because I don't know what its is, and I don't know what change you're talking about. Cameron? Okay, so it's going through a phase change. Okay, and in a phase change, what happens? You go from a solid to a liquid. You go from a liquid to a gas, correct? the energy has to go to doing something, right? So what does it do during a phase change? It doesn't go to make the particles move faster. If it did, their temperature would increase. And you're right, there is something about a phase change that it needs to happen. What did I tell you about the particles in this desk? They're what? What? Close together, packed real tight, right? Why don't the particles of a solid just go flying off all over the place? They do when they become a gas. Why don't they when they're a solid? Why don't things just break apart and fly off wherever they want to go? Okay, it has to get to a certain point to do that. So you're saying it can do that. Can break apart and go flying off all over the place. Okay? Well, then why don't liquids do that? Before they get to the point where they do that. When they're a liquid, why don't they just go flying off in all different directions? Gases do. Why don't liquids? Because there has to be something that's doing what to them? There has to be doing something that's what to these particles in the desk that makes them a solid. Bingo. In a solid, there is something that holds them together. Even in a liquid, there is something that holds them together. But guess what? When you get to be a gas, get away from each other. We call it forces of attraction. We call it forces of attraction. The energy, ladies and gentlemen, down here goes to overcoming forces of attraction, goes to making the particles break apart, to move apart, to move away from each other. Okay? Now, can they get completely free of each other? No, but they can get a little bit more free where they can slide past each other and move around, right? Then they're a liquid. But for a liquid to go to a gas, what do we got to do? We got to break those forces some more. Because there's still forces that hold the liquid together. In a gas, no forces holding it together. It's free to go off in whatever way it wants. In whatever way it wants. The energy always has to go somewhere, ladies and gentlemen. That's where the energy goes. That is where the energy goes. Okay? Now, in the packet that I gave you, ladies and gentlemen, okay, there is a worksheet on a graph like this. Okay? Now, what is happening at B again? What processes? Phase change. Which one? Or which ones? Because there could be two. One going this way, one coming back this way. Which we call? Fusion. What's the other one? Liquid to a solid. And the other one would be going the other direction. What's that called? Oh my gosh, you guys are making this harder than it needs to be. Since you were a little kid, if you put water and made it into ice, we call it freezing. What does everybody complain about in winter? Oh my God, I'm freezing. No, you're not. You're already a solid. How are you freezing if you're already a solid? So what's happening up here? What? What is? The liquid is becoming a gas. What do we call that? Condensation would be gas to a liquid, but I'll take that. No! We do not call it evaporation. Evaporation is a different process. What do we call it? Oh my God, put water on a stove. Boiling. Boiling.
See you tomorrow, Mr. Brand.
Why? You didn't see me today. You took a nap.
Actually, yes, I'd have fit it. It didn't look.
Have a good day, Ray. Yes.
Okay.
Yep. Yep, I'll be around.
Corey Longley to the main office. Corey Longley to the main office. Owen Klopp to the main office. Owen Klopp to the main office.
Come on in, ladies and gentlemen.
Okay, too much.
A little bit. Amari. Oh, and Mr. Brand. I'll be your tour guide for advisory every day. Yep. Who knows where we're going to go today?
I'm gonna go to
Where?
the Bahamas.
The Bahamas. Too hot. Too hot. Too
It's
hot.
cold here.
Go to the Bahamas.
Should have brought a wagon, but at the same time, I don't want to deal with like
Exactly.
this stuff.
Stairs.
Yeah, and this, you know.
Yeah,
Yeah, people riding in it or moving around.
And I realized the stairs are not going to be elevators. Yeah, right.
Good morning, ladies and gentlemen.
Good morning, East High School. And will be prepared and remember it's a great day to be a Red Devil. Before your morning announcement, please stand for the Pledge of Allegiance. I
Pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all.
Attention students, homecoming guest forms are ready in the attendance office and they are due Thursday, September 26th. Any red devils in need of an East t-shirt for homecoming this week can stop in room 235. They are $10 each. We have a variety of sizes, colors, and designs. Are you interested in working together with Our first meeting of the year will be today, September 25th, from 3:15 to 4 p.m. in room 113. We will discuss things.
Hey, listen to the announcements, please. If it kills you, I won't never make you do it again.
If you are interested but unable to attend this first meeting, please stop by 113 anytime or email Mr. Buck. College visit. Thursday, September 26th, 2024, room 8:30 a.m. Monday, September 30th, 2024, UW Milwaukee, 10:30 in the Career Center. Wednesday, October 2nd, 2024, UW Oshkosh, 8:30 in the Career Center. And maybe business in the cafe. Book Club is back. Join us during your lunch for Book Club in the LMC today. This meeting will be used to discuss books that you read over summer as well as books you want to read throughout the year. Do you want to stay during your lunch hour? There are 8 different types of blood. Whether you know yours or not, if you're age 17 or 16 with parent consent, you're just the type to donate. Your East FFA invites you to their fall blood drive on Monday, September 30th, from 8 until 2. If you are age 18, 17, or 16 with parent consent, sign up for a time by going to the website in the announcements and type the sponsor code N398. If you have any questions, please contact the blood drive coordinator, Marissa Collar. Again, donate blood September 30th. Save all the lives. Thank you. Attention all students interested in working in the healthcare field. East has an extracurricular club for you. It's called HOSA, Health Occupation Students of America. Our goal is to help strengthen and support your path to the healthcare industry. We will have an informational meeting today after school in room 133. If you are interested but not able to attend the meeting, feel free to email or stop by and see Mrs. Christopherson with any questions. Hey, Red Devils. Do you want to be a part of the most successful team at the Green Bay East? If so, you should join the academic decathlon team. Decathlon, sorry. Now you may be academic decathlon is only for 4.0 students and is not correct. Okay. We need students of all abilities. We need smart kids. We need the smart kids that let off their grades. Maybe be able to say low. If you're interested, please stop at 235 at 310 o'clock. Tuesday, October 1st, for a brief meeting for information. Congrats to the GBU swim team on beating Manitowoc 116 to 51, with GBU taking first in all events. Congrats to the East Boys soccer team for the come from behind 2-1 win. Also, tomorrow during the food truck rally, the juniors and seniors will be selling root beer floats for $3 outside. Tomorrow is a Rhyme Without a Reason, and we have food trucks during lunch, so stop out for lunch and visit a variety of food trucks that will be out front. Asian food truck, taco truck, Philly cheesesteak, and a dough shop. And it's tomorrow at 7 p.m. Volleyball versus West Pier. Support your team and earn points for your class. Juniors and senior shirts are available in room 235.